Hello and welcome to this talk about geology, metals and green technology. My name is Owen Houlihan and I'm a lecturer in the UCD School of Earth Sciences. I'm going to be talking to you today about the above mentioned topic, but also to alert you to our Bachelor's in Science and Geology, which can be applied for through the CAO system using the code DN200, which of course is that of the Common Entry for Science at UCD. So what is geology? Well, it's the study of this blue ball over here on the right-hand side. It's the study of planet Earth. And mainly that's about studying the materials that Earth is made of. These mainly are composed of rocks, sediments, and various geological fluids like water, of course, and magmas, and various other things, as well as gases that are both above the Earth's surface in the atmosphere, within the hydrosphere, and within the solid Earth itself. So collectively, this comprises the world's largest and oldest repository of chemical, physical, and biological information. So the challenge for us as geologists is to extract out as much of that information as we can in various means and ways, and then to put it together to understand how the Earth works. So essentially, geology is the foundation from which we understand how life, including ourselves, fits into the story of planet Earth and how planet Earth keeps us going. So geology is a very multidisciplinary subject. This is a very nice cartoon which summarizes that. We have lots of people here all around the globe, all around the Earth, the model of the Earth, and they're all trying to figure out various aspects of how the Earth is working. So if we look in carefully, we can see we've got physicists here, for example, here on the top left, or top right, I should say. We've got some physicists, we've got some chemists, we've got people who are doing data science and computational work. We've got mathematicians down here. And we've also got biologists and, of course, geographers, all playing their part in understanding how planet Earth works by measuring various aspects of it and gathering data in various aspects. And in addition to all these different disciplines that come together into geology, there's no small amount of imagination and art which is involved in geology too, because you're taking such a variety of different data sets, all of which may have various gaps and incompleteness, and trying to pull that together into a coherent picture or understanding of not only what's at the surface of the Earth, but also what's underneath it, as shown here in this cartoon up at the top left. So geology is global, and geologists tackle profound and practical questions about various aspects of the Earth on all scales and all across the Earth. So things like plate tectonic motions, geothermal activity, volcanoes and earthquakes. We can also look at things like water and the oceans, how the landscape is evolving, and natural hazards which are associated with the evolution of landscape, and also associated with, of course, volcanoes and earthquakes and other phenomena on the Earth. We can also look at how the solid Earth couples with the oceans, with the hydrosphere, and with the atmosphere. And in doing that, we can understand things about climate change, the drivers of climate change, both in the long term and in the short term. And we can think about how life has evolved, how it originated, how conditions on Earth have changed, and changed life as it has evolved through time and deep geological time. We can also look at things, or we also address things like how to find minerals, also what is the nature of the deep structure of the Earth, what lies beneath our feet, and how old is the Earth, and how it has evolved since it formed. So these are obviously a huge number of big questions that are addressed by geologists. I don't have time to go through all of them, but I will talk to you briefly today about mineral resources and how to find metals that are critical to economic development in the future. So a major driver of economic development at the moment, of course, is the technological revolution. So by 2050, we're expecting to be about 10 billion people on this planet. And if all of those people are to have the quality of life that we have in the more developed part of the world, then of course they need access to technology, and there has to be the components that go into making this technological capability have to be found and have to be resourced from the Earth. So this screen here, or this screenshot, shows you a diagram of all the different chemical components that go into, for example, a smartphone. So we have up here on the top left, we have all the different elements that go into making the screen, for example. Here we have on the top right various electronic components and the elements that go into those. Down the bottom left, we have elements that go into the battery. And over here to the bottom right, we have elements that go into, for example, the casing that holds everything together of the in the device. Now, a lot of these elements, like oxygen, for example, or carbon, are fairly common in the Earth, and so we're not too worried about finding those. But a lot of the elements in this diagram, and particularly the ones that I've circled here, which are metals, are quite rare or expensive to get hold of and put into a phone. So these are elements which are include things like copper, silver, gold, and tantalum, also lithium and cobalt, particularly for the batteries and for storing energy, which we'll talk a lot about more in the talk. So how do we find these energy critical metals, and how do we extract them in a sustainable way? Well, yes, in general, for all resources that we have, so all the built environment, all the clothes you're wearing, all the computer you're looking at, the electronics in your room, everything around you has to be sourced from somewhere. And in general, we can either grow that, for example, cotton going into clothes, or we have to extract it from the earth by mining. And mining, of course, has a bad reputation and a serious public relations problem, in some cases for good reasons. But there are various forms of mining, various ways in which these metals are taken out from the earth and put into our electronic goods. So, for example, lithium is actually extracted nowadays mainly from evaporation of groundwater, salt-rich groundwater in arid environments. So that itself has a lot of challenges, because you have to have you have a sustainability issue with regards to accessing water, which, of course, in such water-challenged areas are needed by other life or other people. We also then have the old traditional method of getting in the ground and digging out some copper and silver and gold deposits, as in here in the Flambeau example from North America. But an important point with this is that mining in itself can be sustainable and can be done in a way which is environmentally sound. So, for example, this Flambeau pit has actually now, since the mining operation ceased, has now been reclaimed and made into, and re-landscaped and made into a recreation and wildlife park. So similarly, if we, instead of digging up big holes in the ground, we look towards more underground mining, we can reduce the environmental and visual impact of mining. And this is exemplified here in Ireland, actually. So this is an image of the Lachine mine in Tipperary when it was operative, down the bottom here. And this is now, you'd hardly even notice there was a mine there, really, apart from the big lake here in the foreground. And even that lake is gone now. If you look at images now of this area, it's mostly fields, because it's mostly been reclaimed since the mining operation ceased. So an alternative source to lithium can be found here in this piece of rock that has been held by David Cater. He's a student in UCD, and he's been looking at an alternative source for lithium in Ireland, at Prospect in County Carlow, where we have this mineral called spodumene, a lithium-bearing mineral. And spodumene can be potentially accessed, therefore, without necessarily recourse to major disturbance of groundwater and pull down of groundwater resources. Another major consideration in terms of the future technological challenges and societal challenges is that of climate change. And as part of climate action, we're steadily moving towards more renewable energy sources like wind and solar. The thing is, though, that in order to do this, we need a hell of a lot of copper. We need lots of copper. In fact, we need 4 to 6 times more copper than we would use in an ordinary nuclear or conventional fossil fuel type electricity system, because we need extra metal for this more distributed system of windmills and solar farms, which need to connect to a grid. So we need a lot more copper, and also we also need to keep an eye on what we're actually building these things on. So, you know, these wind turbines, as you can see in the image here, these are sitting out to sea. They're not floating. They're actually embedded onto the seabed. So we need to know what the seabed is made of, and that's where geologists come in. So this plot here shows the production of copper in millions of tons per annum since about 1900 and going to the modern day, just about 2020, and then projected into the future up to about 2040. And a major take home from this graph is you can see that the production of copper has been steadily or exponentially increasing almost over the last 100 years or so. But an important point from this graph is that the projected amount of copper that's going to be needed, about 746 million tons of copper, is going to be needed in the next 20 to 30 years. That amount actually will probably exceed all of the copper that's been mined in history up until now. So we have a huge challenge to find this copper in order to implement our goals for climate change and mitigation of climate change. So this is a major problem, and it is actually the focus of ongoing research at UCD School of Earth Sciences and as part of the Irish Centre for Research in Applied Geosciences, or ICRAG. So this is an example from Professor Murray Hitzman of ICRAG of a copper and cobalt deposit in the Central African Copper Belt, which is under investigation by UCD researchers at the moment. So in addition to generating and transmitting electricity by renewable methods and the resource issue that raises, we also have to find ways to store energy, store electricity, because electricity generated by wind and solar is intermittent. That means, for example, that we don't have a steady supply of electricity from those sources, because of course you don't generate so much solar power if the sun isn't shining, and you don't generate so much wind power if the wind isn't blowing. So in times when we don't have a lot of wind or a lot of sun, we need a way to store the energy that's generated when we do have lots of wind and sun, in order to facilitate a consistent sourcing of light and heat. And also, fundamentally, we need to be able to store electricity in order to power our transportation network, which of course is a major challenge in itself to try and wean away from fossil fuels. So the challenge here is that not only are metals like cobalt and lithium, they're quite scarce and difficult to find, they're also quite expensive. So we're looking for alternative metals that we can use in batteries. And one of these options is zinc, actually. This is a recent paper from Science in 2017, which reported on a new way of designing zinc batteries, such that actually their performance levels are equivalent to lithium batteries. And this is really potentially quite an important discovery, because the zinc is a much cheaper metal at the moment and is not so scarce as lithium. So where do we get the zinc? Well, if you're a geologist, you'll know that zinc is mainly found as an ore called, or a mineral called sphalerite, which is the brown bands shown here in this image to the top left of the screen. The purplish metallic bands are actually another mineral called galena, which hosts lead. And where we find this actually is in Ireland. So Ireland has some of the best, or had some of the best, lead and zinc deposits in the world. World-class lead and zinc exploration territory is Ireland. And these yellow dots on the map of Ireland here show areas or sites that were mined commercially for lead and zinc. Currently, we only have one mine left in Ireland, which I'll talk about in a minute. This map to the right-hand side is a geological map showing rocks of various ages. And the key point in this map, which I'll show you, is these black lines which run through here. These are faults. These are big fractures running through the rocks, which have been developed about 300 million years ago, as the area of Ireland was being stretched roughly northwest to southeast here. So if we take a three-dimensional view of those fault structures, and what researchers have been doing in UCD is trying to understand how those fault structures relate to mineral deposits hosting lead and zinc. So here in this cartoon, we can see the faults going down deep under the ground, up to several kilometers below the ground surface, and offsetting various layers here, as you can see. And then the idea is that there are fluids circulating here under the ground, and these fluids are actually bringing up the minerals through the rocks and then using the faults as conduits to go up to higher levels in the earth, where eventually the fluids allow the lead and zinc to drop out as solid mineral forms, like you see in the top left in the photograph there. So where do we actually see that in Ireland? Well, at the moment, there's only one operational mine in Ireland. This is at Navan, and if you were to drive around Navan, you'd hardly notice it was there, really. In fact, it's because mostly it's deep under the ground. It's the third largest lead and zinc mine in Europe, and it's now down excavating at about 1 kilometer under the ground. So we can see this kind of, at the top of the slide here, you can see this oblique view of Navan from Google Earth or satellite image. And if we now imagine taking a slice down through the earth under Navan using seismic imaging, this is what we might see. So over here on the left-hand side, you can see this area where we've got these blue lines. These represent exploration boreholes. These blue lines drill down under the ground. And you can see we've got these zones of red and black reflections here. These are reflections or layers or horizons which are reflecting back seismic waves that are being bounced around in here, and they're reflecting back to the surface and picked up in sensors of the surface. So we can make an image of what the subsurface structure beneath Navan looks like. And from that, you can see that where the mining is operational here, you have these very strongly colored, very bold black and red zones. These represent very strong reflections from under the ground. And then you can see that continues towards the bottom right of the image here. And this is where we might have suspected that there could be similar deposits under the ground. And indeed, this was confirmed subsequently in 2012 when there were drillings that were undertaken down to very deep depths, down into these reflective areas and below them, down to about 1.5 kilometers under the ground or slightly more. And here we found a new lead and zinc deposit, or an extension of the existing deposit, which is now going to extend the life of this mine. It means we don't have to try and find it somewhere else. Another example of how UCD research is used to understand lead and zinc deposits is back with the example of Lachine. So here I'm going to quickly show you this animation, or this video here, which shows a 3D animation of the Lachine lead and zinc deposits. What we have here is, this is actually a geological layer, or top of a geological layer deep under the ground. We can see that its elevation here in meters. Again, this is below the ground. You can see that it's highly elevated on one side with these red zones. It's dropped down to a lower level here in the blue zones, and you can see that how it's managed to be dropped down is along these grey plains, which are the faults that I mentioned earlier. These are these fractures which are which one side of the rock has slid down to a lower level. And then you can see that the minerals seem to be these kind of metallic purplish areas. You can see that they're coming away off from the faults. So using a really amazing set of borehole data and other information, we can understand then the three-dimensional geometry of the body, and also then how it's affected by these pre-existing fracture systems. So what we can see here in grey is the outline of the ore body at depth at Lachine, and these various geological fractures and faults are shown in various colors here. And if we move to the next slide, what I can show you is that this is the concentration of copper in the ore body as reconstructed by researchers in ICRAG at UCD. So here we can see in the warm colors, in the yellows and the reds, we have high concentrations of copper. You can see the copper concentration is especially high over next to these big faults. So again, this is supporting the idea that the fluids have come up along the faults and dropped out the copper adjacent to the fault first, and then flowed out into the rocks surrounding the fault with time. And you can see here the zinc concentrations, similar pattern. Again, we have the highest concentrations of zinc closest to those green and purple lines and red lines, which are the faults in this map. So by studying Lachine, an Irish example, a world-class lead and zinc deposit, we can figure out what the characteristics are that will enable us to find similar or even better and bigger deposits either in Ireland or elsewhere in the world. And this will help us to provide the raw materials that may be needed for challenges associated with green energy transition in the future. So in general, geology and sustainability actually go hand in hand on many, many levels. This is a diagram which is a summary of the UN Sustainable Development Goals. And as you can highlight here with these circles, geology is directly involved in achieving more than half of the UN Sustainable Development Goals, and indirectly in several more. So I've mentioned many of them through this talk now. For example, affordable and clean energy, economic growth, industry innovation, sustainable cities and communities are all requiring sources of metals that will power this into the future. But other aspects like clean water, sanitation, climate action, life below water, life on land, I simply haven't time to talk about right now. But geology is also heavily involved in all of those. So I'll leave you here with this last slide, which to remind you that if you want to study for geology, we'd love to have you at UCD. This is a picture here of our geology students from UCD who are investigating a raised beach in southern Spain. This has now been consolidated into solid rock. It's not very old at all, and it probably indicates that this area has been undergoing a lot of tectonic uplift in the last few years, or few thousands of years, and probably still ongoing. And that's a whole other subject I don't have time to talk about right now. But if you have any questions or you are interested in learning more about our geology degree, you can email us at geology@ucd.ie, And remember that the CAO code, is DN200, the common entry for science at UCD. So thank you for listening. I hope you enjoyed it, and take care. Bye-bye.